Welcome back. In this video, we're going to look at examples of monotonic and bounded sequences. Let's get to it. All right, so here's our first example. We want to know, does the sequence a sub n equals 1 divided by 3 to the power of n converge? And so the way we're going to determine if this sequence converges in this video is by determining if our sequence is both monotonic and bounded. You can always, of course, take the limit of your sequence to see if it converges to a specific value, but in this video we're going to focus on an alternative method to determining the convergence of a sequence that is based on a particular theorem. And that theorem says this: if a sequence a sub n is bounded and monotonic, then it converges. And so what we're going to do for all the sequences in this video is test them to see if they are both monotonic and bounded. So we're going to be checking both of those requirements. So the first thing that I'm going to test for our sequence here is if it's monotonic. And all that means is, are the terms of our sequence increasing or decreasing? If we can show that they are decreasing or increasing, then our sequence will be monotonic. And so let's take a look at the first couple terms of our sequence here. A sub 1 will be equal to 1 divided by 3 to the power of 1. So I have 1 divided by 3 to the power of 1. That will be equal to 1/3. Then for a sub 2, that will be equal to 1 divided by 3 squared, and that's equal to 1/9. And then a sub 3 will be equal to 1 divided by 3 cubed, and that's equal to 1/27. And then let's do one more term. A sub 4 is equal to 1 divided by 3 to the 4th power, which is equal to 1 divided by 81. All right, now 1/3 is approximately equal to 0.3 repeating. 1/9 is approximately equal to 0.1 repeating. 1/27 is approximately equal to 0.037 and some more decimals. And 1 divided by 81 is approximately equal to 0.0123 and some more decimals. All right, now if we look at these values for a sub 1 through a sub 4, we can see that the terms are slowly decreasing, right? We have 0.3 repeating, and then 0.1 repeating, that's less than 0.3. Then we have 0.037, which is less than this term, and then 0.0123, which is less than this term. And so each of our subsequent terms are getting smaller, and so it seems that our sequence is decreasing. But now we have to show that that's true in order to conclude that our sequence is monotonic and that it's decreasing. And so the way we're going to show that, or prove it, is by using the following statement or inequality. Now before I write it down, remember we're trying to show that this sequence is decreasing with every term. And so if we have a term a sub n, that's going to be greater than or equal to the next term a sub n plus 1. And so this is what we want to show is true for this sequence, that the preceding term is greater than the next term, meaning that each subsequent term is getting smaller. Now a sub n we know is 1 divided by 3 to the power of n, so we have 1 divided by 3 to the power of n, and that will be greater than or equal to a sub n plus 1. So we'll have our nth term, but we're going to replace n with n plus 1. So we have 1 divided by 3 to the power of n plus 1. Okay, and so now we want to show that this statement is true by simplifying it into a form that we can verify is true. And so the way we're going to simplify it is to cross multiply. We'll multiply 3 to the power of n plus 1 times that one, and that will be on this side of the inequality. And then we'll multiply 3 to the power of n times this one, and that will be on this side of the inequality. So we'll have 3 to the power of n plus 1 is greater than or equal to 3 to the power of n. Okay? Now if we simplify this exponential function right here, we can split it up into two parts. We could have 3 to the power of n times 3 to the power of 1, and that will be greater than or equal to 3 to the power of n, right? The reason we can do that is if you have the same base and they have exponents, when you multiply them together, you add the exponents, and so 3 to the power of n times 3 to the first power will be equal to 3 to the power of n plus 1. We added those exponents. And so we can reverse that process and go from 3 to the power of n plus 1 to 3 to the power of n times 3 to the first power. Now the reason we do that is because now we have 3 to the power of n on both sides of the inequality, and so if we divide both sides by 3 to the power of n, we will be left with 3 to the first power, or just 3, and that it's greater than or equal to 1, right? We divided 3 to the power of n out from this side of the equation, And then on this side, 3 to the power of n divided by itself is 1. And so now we have this statement that 3 is greater than or equal to 1, and all you have to ask yourself is that a true statement? Is 3 greater than or equal to 1? Well, 3 is greater than 1, and so yeah, this is a true statement. And so since that is true, we have now just shown or proved that this sequence is decreasing. We have shown that a sub n is greater than or equal to a sub n plus 1. Every subsequent term is going to be smaller than the previous term. All right, and so what we can say is that our sequence, a sub n, is monotonic. And specifically, it is decreasing. So you might want to make a note of that as well. Okay, so that's one half of this problem. In order to determine if the sequence converges, it not only has to be monotonic, but it also needs to be bounded. And so that's what we're going to check next. And the way we're going to check that is by looking at a graph of this sequence. And so here's how that's going to look. We're going to have a vertical axis and a horizontal axis. The horizontal axis will be our values of n, and the vertical axis will be the value of our terms, a sub n. Now I'm just going to plot the 4 terms that we found. So that will be for n equals 1, n equals 2, n equals 3, and n equals 4. And a sub 1 was equal to 1/3. So I'm going to label that right here. That's going to be 1/3. And so our first term will be right there on the graph. Then we have a sub 2, which is 0.1, and that's going to be even further down on our graph. Then a sub 3 is 0.037, and so that's even further down, but still greater than 0. And then a sub 4 is 0.0123, which is even closer to 0. And so the graph of our sequence looks something like this. All right, now the reason why this is helpful is it gives us a visual of whether our sequence is bounded or not. And what it means for a sequence to be bounded is that there needs to be some upper limit or some upper value for which the sequence will never surpass, meaning it's always less than or equal to some value, and there needs to be some lower bound or some lower limit that the sequence will never go below. Essentially, what we're saying is that all of the terms of the sequence are going to lie between 2 specific values. If we can't see that the sequence is bounded by some upper bound and some lower bound, then it's not bounded and we can't conclude if the sequence converges. So if we look at this graph here, is there an upper bound and a lower bound for our sequence? Well, let's start by looking at the lower bound. We can see that our terms are getting closer and closer to 0, and so it would be a good guess to say that 0 is the lower bound. But a better way to know that 0 is the lower bound, a value that your terms are never going to be lower than, is to just look at your sequence, 1 divided by 3 to the power of n. We're only going to be plugging in positive values of n because a sequence starts at n equals 1 and increases towards infinity. And so 1 divided by 3 to the power of n is always going to be positive. It's never going to be a negative value, and so these terms are never going to drop below 0. And so 0 is going to be the lower bound for this sequence. None of our terms are ever going to have a value lower than 0. And so I'm going to label that with this line here. This represents our lower bound that we label with the letter capital N. That's just the letter we use for the lower bound. And so what that means is that our sequence, a sub n, is always going to be greater than or equal to that lower bound of 0. All right, but now what about an upper bound? Is there a value for which the terms of our sequence will never be greater than? Well, if you look at the graph here, we know that the terms of our sequence are decreasing, and so they're never going to rise back up, and so the highest value a term could be will be the value of our first term, because it's only going down from there, right? So when n equals 1, we have the highest value a term will ever be, and so 1/3 is the value of that first term, and so 1/3 will be the upper bound. We're never going to have a term greater than 1/3. And so right here is our upper bound, and we label that with a capital M, and M is equal to 1/3. And so our sequence will always be less than or equal to that value of 1/3. You will never have a term greater than that value. And so now we have that our sequence is bounded below by 0 and bounded above by 1/3. And so since it is bounded on both sides, we can conclude that our sequence is bounded. And so I'll write that a sub n is bounded. Okay, so we have found that our sequence is monotonic, specifically that it's decreasing, and we have found that it is bounded. And so because it is both monotonic and bounded, we can conclude that our sequence converges. And so that is our final answer. We will say that the sequence A sub n converges. All right, let's look at another example. So here's our next example. We want to know, does the sequence A sub n is equal to n squared divided by n plus 1 converge? So we're going to go through that same process we went through for the first example. We're going to start by determining if our sequence is monotonic, and then we're going to see if it's bounded. And so let's start by writing out some of the terms of our sequence to get an idea of if the terms are increasing or decreasing. And so A sub 1 will be equal to 1 squared divided by 1 plus 1, right? We're just plugging in that value of n for n in our sequence. And so that's equal to 1 half, because 1 plus 1 is 2 and 1 squared is 1. And I'm just going to write the decimal values as we go as well. That's equal to 0.5. And then A sub 2 will be equal to 2 squared divided by 2 plus 1, and that will be equal to 4 thirds, and that's equal to 1.3 repeating. Then for A sub 3, that's going to be equal to 3 squared divided by 3 plus 1, and that will be equal to 9 divided by 4, and 9 fourths is equal to 2.25. And then let's do one more term. A sub 4 is equal to 4 squared divided by 4 plus 1, and that is equal to 16 fifths, which is equal to 3.2. All right, and so those are the first 4 terms of our sequence, and so let's see if we can identify a pattern within our terms. We have 0.5, then 1.3 repeating, that's greater than 0.5, then we have 2.25, that's greater than 1.3 repeating, and then we have 3.2, which is greater than 2.25. And so it would seem that with each subsequent term, the terms are getting larger. Our sequence is increasing with every term. And so we can see that they're increasing, but we do need to prove it. We need to show that that is true. And so we're going to use a similar statement to what we used in the previous example. Our inequality will look a little bit different though, because these terms aren't decreasing like our previous sequence. These terms are increasing. And so what we want to show is that A sub n is less than or equal to the next term, A sub n plus 1. Okay, so for our sequence, we want to show that a term A sub n is going to be less than the next term because it's increasing. That next term should be bigger than the previous term. And so A sub n is n squared divided by n plus 1. So we have n squared divided by n plus 1, and that will be greater than or equal to A sub n plus 1. And so if we replace n in our sequence with n plus 1, we will have n plus 1 squared in the numerator divided by n plus 1 plus 1. All right, so now if we simplify a little bit, n plus 1 plus 1, those 1s are just going to combine, and so we'll have a denominator of n plus 2. So I'm just going to rewrite that here. We will have n plus 2, and then we want to simplify our inequality to a point where we can see if it's true or not. And so let's cross multiply again, just like we did in the previous example. We're going to have n squared times n plus 2, so I'll just write out n squared times n plus 2, and that will be less than or equal to n plus 1 times n plus 1 squared. So we will have n plus 1 times n plus 1 squared. Now, in order to compare both sides of this inequality, we're going to want to expand everything as much as possible. So I'm going to clean up my work a little bit here to get some more space. And then let's start by distributing n squared through this quantity. So we'll have n squared times n, that's n cubed, and then n squared times 2 is 2n squared. So we have plus 2n squared, and that will be less than or equal to n plus 1 times n plus 1 squared. Now, before we can multiply n plus 1 by this quantity, we need to square this quantity first. So we'll have n plus 1 times n plus 1 squared. Now, I'm going to use a shortcut to square this factor quickly. What we're going to do is square the first term, so that will be n squared. Then we're going to add 2 times both of these terms multiplied together. So n times 1 is n, and so we'll multiply 2 by n. And then we'll add that to our last term, which is 1 squared. And 1 squared is 1. Okay? And so now we want to multiply n plus 1 times n squared plus 2n plus 1. So we're going to have to take turns multiplying each of these terms by each of these terms. So we're going to have n cubed plus 2n squared is less than or equal to n times n squared. that's going to be n cubed. Then n times 2n, that's going to be plus 2n squared. Then we'll have n times 1, which is just n, so plus n. And then we're going to multiply 1 by each of these terms, and so we're just going to have each of these terms. So we'll have plus n squared plus 2n plus 1. All right, and so now notice on both sides of the inequality, we have n cubed and 2n squared, and so we can subtract those terms from both sides of the inequality, and so we can just cross those out, and what we're going to be left with is 0 is less than or equal to these terms, but note that we have two like terms of 2n and n, and so that's going to be 3n, so we'll have n squared plus 3n plus 1. All right, and so now there's no reason to further simplify this. We can actually determine if this statement is true based on this inequality right here. We have 0 is less than or equal to n squared plus 3n plus 1. And we know that for our sequence, n is going to be greater than or equal to 1. We start our sequence with n is equal to 1, and so if we plug 1 in for n here, and then any value of n after that, this is always going to be greater than 0. It's never going to be less than 0, and so this statement is true. And so we have just shown that this sequence is an increasing sequence and that it is monotonic. And so if I clean up my work, we can now say that a sub n is monotonic. And then specifically that it's increasing. Okay? And so now let's check to see if this sequence is bounded. And so let's draw a graph so we can visualize this. Remember that the vertical axis is the value of our terms, and the horizontal axis will be the value of n. And so I'm going to plot the first four terms here. So we'll have n equals 1, n equals 2, n equals 3, and n equals 4. And then I'm going to label this side with 3, 2, and 1. And now a sub 1 is equal to 0.5, and so that's when n equals 1, and 0.5 is right about there. So we will have our first term there. Then a sub 2 is 1.3 repeating, so that will be right about there. And then a sub 3 is 2.25, and so that will be right about there. And then a sub 4 is 3.2, and so that will be up here. All right, so you can see that with each subsequent term, the value of those terms is increasing, just like we found. And so can we conclude that this sequence has an upper bound and a lower bound? Well, we know it's going to have a lower bound, right? Because this sequence is always going to be positive. We're never going to have a term that is less than 0. And so we know that this sequence is bounded below by 0. And so I'll represent that with this boundary line right here. That will be our lower bound of n, which is equal to 0. So our sequence, a sub n, is going to be greater than or equal to 0. But now, does it have an upper bound? Well, if we look at our graph here, each of our subsequent terms is getting larger, and that's going to increase for forever. So there's actually going to be no upper bound that will limit the value of the terms of our sequence. Those terms are just going to keep getting larger and larger, and so it's not bounded above. And so because this sequence is only bounded below and not bounded above, we cannot conclude that it's bounded, and therefore we can't conclude that it converges. All right, so we can say that our sequence, a sub n, is not bounded, and our test of convergence, based on if it's monotonic and bounded, is going to be inconclusive. We do not know if this sequence will converge just based off of those two factors. And so this might be a sequence where determining its convergence would be easier by using a limit, because if you would use a limit on this sequence, you would find that it is approaching infinity, and so then you would know that the sequence diverges. It doesn't converge to any value. Okay? So you would know that from the limit, but you would not know that from the test that we are doing here. Just because a sequence isn't both monotonic and bounded doesn't necessarily mean that it doesn't converge. So you can't just say that this diverges because it's not both of those things. You would have to test it some other way first. All right, so here's our next example. We want to know, does the sequence a sub n is equal to cosine of n divided by n converge? All right, and so the first thing that we want to do is write out some of our terms. And so I'm going to write them out like this time. Our first term, a sub 1, will be cosine of 1 divided by 1. Our second term, a sub 2, will be cosine of 2 divided by 2. Our third term will be cosine of 3 divided by 3, and we could continue this on for a couple more terms here. I'm going to stop at cosine of 5 divided by 5, but you could continue on from there. All right, now the decimal value for each of these terms are going to be the following. Cosine of 1 is approximately 0.5403. Cosine of 2 divided by 2 is approximately negative 0.208. Cosine of 3 divided by 3 is approximately negative 0.330. Cosine of 4 divided by 4 is approximately negative 0.163. And cosine of 5 divided by 5 is approximately 0.057. So now if you look at the value of our terms here, can you conclude that we are either increasing or decreasing, meaning that the sequence would be monotonic? Well, our first term is a positive value of 0.54, then our next value is negative 0.2, so it decreased. Then we have negative 0.3, so it decreased further. And then we have negative 0.16, so it increased. And then we have 0.057, where it increases again. So we started out decreasing, and then we increased, and so it's not the same thing happening with every single term. Every single term is not getting smaller, and every single term is not getting larger. And so we cannot say that this sequence is monotonic. Every single term would need to be getting larger or getting smaller for it to be monotonic. And we should expect that this wouldn't be monotonic because of the cosine function. Remember that cosine oscillates between positive 1 and negative 1? If you were to look at the graph of cosine, it would look something like this. It would keep oscillating around the x-axis from the values of y equals positive 1 and y equals negative 1, and so it makes sense that these values would also oscillate between being positive and negative. Okay, and so because of that, we will say that a sub n is not monotonic. Okay? It oscillates between positive and negative values, meaning that it increases and decreases and increases and decreases. It doesn't just go one direction. Okay? And so we could stop right there and say that, well, this test isn't going to work. We cannot conclude that this sequence converges based on if it's monotonic and bounded. But let's just see if it's bounded anyway. It would be good practice to see if we can determine if this sequence is bounded. And so if I draw our axes here, this will be a sub n. And then our other axis will be n. And so we have n is equal to 1, n is equal to 2, n is equal to 3, n is equal to 4, and n is equal to 5 for our 5 terms. And because the cosine function oscillates between negative 1 and positive 1, we know that none of our terms are going to be greater than 1 or less than negative 1. And so those are the two values I'm going to label along our vertical axis. And now let's plot our terms. A sub 1 is 0.5403. That's going to be about right here, about halfway between 0 and 1. Then a sub 2 is negative 0.208. I'll say that that's right about here. And then we have negative 0.33 for a sub 3. So that's maybe right there. Again, this isn't quite drawn to scale, but it should get the point across of what kind of shape we have here with our terms. So if we move on to a sub 4, we have negative 0.163. That'll be right about here maybe. And then a sub 5 is 0.057. And so now we're back into positive values. And so you can see this oscillation. We decrease and then we increase. And this would continue on forever as we would pick larger and larger values of n. All right, now I actually already explained this earlier. We know that none of these terms are going to be greater than 1 or less than negative 1 because the cosine function oscillates between those two values. And so if you're dividing 1 or negative 1 by some value n, it's always going to be less than 1 or greater than negative 1. Okay, and so those are actually our bounds. Positive 1 is our upper bound that we label with the capital letter M, and negative 1 is our lower bound that we label with the capital letter N. And so we would say that a sub n is greater than or equal to negative 1 and less than or equal to positive 1. It is bounded below by negative 1, but bounded above by positive 1. And so this sequence is bounded. A sub n is bounded, so we could write that. A sub n is bounded, but we cannot conclude that it converges based on that because it's not monotonic. All right, and so you might be tempted to say that this sequence diverges then, but that's actually not the case as we would plot out more and more of these terms, they would get closer and closer to zero. It would still oscillate between positive and negative values, but they would be positive and negative values that are getting closer and closer to zero. And so while this method of determining convergence is inconclusive, we don't know if it converges based off the fact if it's monotonic and bounded, but we could determine that it's convergent if we took the limit of this sequence. And I believe I take the limit of this exact sequence in a previous video, and we did find that it converges to zero. In fact, I think we might have used the squeeze theorem to determine that. All right, so sequences like this, where the test of it being monotonic and bounded is inconclusive, using the limit to determine its convergence is going to be a better way to go. All right, and so with that, let's look at one more example for this video. Okay, so here's our last example. We want to know, does the sequence a sub n is equal to 2 to the power of n divided by n factorial converge? All right, and so what we want to do is see if it's monotonic and bounded. And so we'll start by determining if it's monotonic. Let's write out some of the terms of the sequence. We know that a sub 1 is going to be equal to 2 to the power of 1 divided by 1 factorial. A sub 2 will be equal to 2 to the power of 2, or 2 squared, divided by 2 factorial. A sub 3 will be equal to 2 cubed divided by 3 factorial. A sub 4 will be equal to 2 to the 4th power divided by 4 factorial. And then let's do one more. A sub 5 will be equal to 2 to the 5th power divided by 5 factorial. Now to simplify them, a sub 1, we have 2 to the 1st power. That's just 2 divided by 1 factorial. That's just equal to 1. So this is equal to 2 divided by 1, which is equal to 2. Then for a sub 2, we have 2 squared, and so in the numerator we have 4, and in the denominator we have 2 factorial, which is 2 times 1, and so this is equal to 4 divided by 2, which is 2, and that's the same as our previous term, so that's a little bit weird, but we'll talk about that. Let's finish simplifying the rest of our terms first. A sub 3 will be equal to 8, because 2 cubed is 8, divided by 3 factorial, so 3 times 2 times 1, that's equal to 6. So this is equal to 8/6, which reduces to 4/3, which is equal to 1.3 repeating. Then for a sub 4, this is equal to 16 divided by 4 factorial. So we have 4 times 3 times 2 times 1. That is equal to 16 divided by 24, and that reduces to 2/3, which is equal to 0.6 repeating. And then for our last term, a sub 5, this will be equal to 32. That's 2 to the 5th power divided by 5 factorial, which is 5 times 4 times 3 times 2 times 1, and that is equal to 32 divided by 120. And that reduces to 4/15, and that is equal to 0.26 repeating. Okay, so now that was a lot of work, and so if I clean this up a little bit, here are the 5 terms that we just found. A sub 1 is 2, a sub 2 is 2, a sub 3 is 1.3 repeating, a sub 4 is 0.6 repeating, and a sub 5 is 0.26 repeating. All right, and so now can you conclude that these terms are either increasing or decreasing? Well, after the first 2 terms, which are exactly the same, they're both 2, our terms look like they're decreasing. We have 2, then 1.3 repeating, that's less than 2, then 0.6 repeating, that's less than 1.3 repeating, and then 0.26 repeating, which is less than 0.6 repeating. And so each subsequent term after the first 2 terms is getting smaller. And so even though these first 2 terms are the same, this still lines up with the definition of being a monotonic sequence. If you watch the lesson video, you know that for a monotonic sequence, we could also say, instead of increasing or decreasing, that a sequence is non-decreasing or non-increasing, meaning that for an increasing sequence or non-decreasing, that each subsequent term would either be greater than or equal to the previous term, and for a decreasing sequence or a non-increasing sequence, each subsequent term would be less than or equal to the previous term. And so for this sequence, we have terms that are less than or equal, for these 2, to the previous term. And so our terms match that definition, and so we are fine to say that this sequence is still decreasing, or more correctly, you would say that it's non-increasing. Our terms are not getting larger, they're getting smaller or staying the same. And so let's prove that. What we want to show is that a sub n is greater than or equal to the next term, a sub n plus 1. Right? The next term, a sub n plus 1, needs to be less than or equal to the previous term, a sub n. And so let's show that this is true. We know that a sub n is 2 to the power of n divided by n factorial. So we have 2 to the power of n divided by n factorial, and that is greater than or equal to a sub n plus 1. So we will replace n in this sequence with n plus 1, and so we have 2 to the power of n plus 1 divided by n plus 1 factorial. Okay, and so now we want to simplify this inequality so that we can see that the statement is true. So if we cross multiply, we'll have 2 to the power of n times n plus 1 factorial. So I'll write that, 2 to the power of n times n plus 1 factorial, and that is greater than or equal to n factorial times 2 to the power of n plus 1. So we have n factorial times 2 to the power of n plus 1. Now to further simplify, let's start with this side of the inequality. We can break up 2 to the power of n plus 1 to be 2 to the power of n times 2 to the first power. Right, remember that we can break up that exponent because 2 to the power of n times 2 to the first power can be simplified by adding those exponents, which would be n plus 1. So we can reverse that process to have 2 to the power of n times 2 to the first power. And that's still multiplied by n factorial. And so then let's work on the other side of the inequality. We can actually simplify this factorial in a way that will be helpful. Remember that 4 factorial is equal to 4 times 3 times 2 times 1. You could also write that like this. 4 factorial is equal to 4 times 3 factorial, right? Because 3 factorial is 3 times 2 times 1. So these are the same thing, just written in a different way. And so you could rewrite a factorial by subtracting 1 from that value and then just having the factorial after that value. Right, so we could rewrite 4 factorial with 4 times 3 factorial, so we can write n plus 1 factorial by multiplying n plus 1 times n plus 1 minus 1 factorial. Right, so here's what that looks like. We have 2 to the power of n times n plus 1 times n plus 1 minus 1 factorial. Right, we subtract 1 from that value, just like we did here. 4 times 3, which is 1 less than 4, and that's where the factorial is, but 1 and negative 1 cancel out, and so we just have n factorial. And so let's rewrite this whole thing. What we actually have is 2 to the power of n times n plus 1 times n factorial. This is the way that we can rewrite n plus 1 factorial. Okay, and so by doing that, we now have n factorial on both sides of the inequality, and so if we divide both sides by n factorial, those will be eliminated, and the same thing is going to happen for 2 to the power of n. We have 2 to the power of n here, and 2 to the power of n over here, so if we divide both sides by 2 to the power of n, those will also be eliminated, and so we're just going to be left with n plus 1 is greater than or equal to 2. Right, this is 2 to the first power, which is just 2. And so now if we subtract 1 from both sides, we will have that n is greater than or equal to 1. Right, 2 minus 1 is 1. And so we have n is greater than or equal to 1, and is that a true statement? And the answer is yes. For a sequence, the first value of n is 1, and then we increase from there. All of the values of n for a sequence are greater than or equal to 1. And so this is a true statement, which means that we have proved that this sequence is monotonic and that it specifically decreases, or the terms are non-increasing. Because remember, those first two terms were the same thing, and so we would say it's non-increasing rather than decreasing. Essentially, our terms aren't getting larger, they're either staying the same or getting smaller. Okay, and so what we can say is that our sequence, a sub n, is monotonic. Specifically, we can say that it is non-increasing. Or you could just say decreasing if you'd like, but non-increasing is going to be more accurate in this scenario. Okay, so now that we know that our sequence is monotonic, we now need to test to see if it is bounded. And that will determine if we can conclude that the sequence converges. Okay, so let's graph our terms here. Remember that the horizontal axis are the values of n, and the vertical axis will be the value of our terms, a sub n. And we have 5 terms to plot. So we have n is equal to 1, n is equal to 2, n is equal to 3, 4, and 5. All right, now a sub 1 is equal to 2, so that's going to be the first term that we plot. A sub 1 is 2, but then a sub 2 is also 2, so that's going to be right there as well. Then a sub 3 is 1.3 repeating, so if this is 1, then we'll say that 1.3 repeating is right about there. Then a sub 4 is 0.6 repeating, so we'll say that that's right about there. And then a sub 5 is 0.26 repeating, which is maybe there or so. Okay, so what we can see is that our terms are decreasing here after that second term, just like we concluded that it's monotonic. But can we conclude that this sequence has an upper limit and a lower limit? Well, if it's going to keep decreasing after that second term, and both a sub 1 and a sub 2 are 2, well, that means that the terms of our sequence are never going to be larger than 2. Our first two terms were 2, but that's it. And so we would say that 2 is our upper bound. That is going to be our value of m. Okay, so our sequence, a sub n, is bounded above by 2, but is it bounded below by anything? Well, all of our terms are going to keep decreasing and get closer to 0, but will they ever pass 0? Well, the answer to that is no. We're never going to have a negative value because this sequence is always going to be positive, right? The values of n that we plug into this sequence start at positive 1 and increase towards infinity, and so this sequence will always be positive, which means it's bounded below by 0. We will never have a term of our sequence that will be below 0. And so I'll label that 0 is our lower bound, capital N, and so our sequence is bounded below by 0. And so the terms of our sequence are going to lie between 0 and 2. They will never be greater than 2, and they will never be less than 0. All right, and so we have concluded that a sub n is bounded. Since it is bounded above and below, it is bounded. And so now we have found that our sequence is monotonic, specifically non-increasing, and it's bounded, and so via that theorem, we can conclude that this sequence converges. And so we can write that a sub n converges. Okay, and so that is the final answer, or the final conclusion to this problem. We were able to determine if this sequence was monotonic and bounded, and because we could, we can say that it converges to some value. And if you were to look at the limit of that sequence, you could determine that it is approaching 0, and so it does converge to 0, but we wouldn't know that by using this test. We would have to use a limit to find that specific value. Okay, and so if you haven't seen that, be sure to check out my previous lesson and examples video where we looked at converging and diverging sequences. Okay, and so with that, this was the last example for this video. If you have any questions, feel free to leave those in the comments, but if you don't have any questions, this is all I had for now, so I will see you next time.